Computer audio. Start video. Hey, we've got Phoebe on board already. Great. Wonder if there's anybody else. Nope, Phoebe, it's just you and me right now. Here's your chance for one-on-one instruction. Do you have any questions? I'm trying to adjust this picture here. Yeah, okay. There we go. And I guess that's the way it's going to be. Phoebe, unmute and say hi. Earth calling Phoebe, Earth calling Phoebe. Come in, Phoebe. Let's see what we're going to study tonight. The big topic is Kirchhoff's voltage law. We have several topics for tonight, but probably the big topic, well, there's several topics. There's equivalent circuits. There's Kirchhoff's laws. Those are two big topics. Wonder what else there is. Let's see if anybody else is on board. Phoebe, it's just you and me, and class starts in 2 minutes. Here's your chance to ask me something.
Well, I'm going to be driving, so I'll just have where I can hear you.
Oh, you just be careful. Yeah.
Okay.
You be careful. Well, I was also going to tell you guys about ammeters and voltmeters. Well, we got enough to keep us busy, really. Now let me write down the homework. The homework. I sure hope we can get some more students. In 2 minutes, class start. Oh, there's Nicholas. Nicholas is with us. All right. Good. This is homework number 7. What it is there's a problem from 9 and a problem from chapter 10. Now, these are due Friday. Today's Tuesday, right? I get mixed up. Yeah, it's Tuesday. Tuesday the 29th. And these are due Friday. It's in the on the blackboard. You can look that up. Well, I'm ready to talk about equivalent circuits. And let me last check on who we have here. We just have, hey, we got Zach now. Zach is with us, Phoebe and Nicholas. And some more will show up here in a little bit. What I wanted to do was problem 1069 and show you equivalent circuits. And let me find it. Problem 1069. All right. I found it. There it is. And here's our circuit. Okay, now this is in the book. It's problem 1069. It's on page 491. Now let's put some numbers on here. Now you got to understand this is the internal resistance of your battery. See, the battery has what they call an EMF of 30 volts. EMF stands for electromotive force. It's unfortunate because it's not a force. If it was a force, EMF would be in newtons. But EMF is in volts. But they named it that. It's what the battery would have if there's no load on it. But see, the actual terminals, this is the positive terminal. Here, let me put that a nice red color here. There's your positive terminal. And down here, that's your negative terminal of your battery. See this whole thing here is your battery. You know, batteries have a positive and a negative terminal. Now that 30 volts, what that is if you measured your battery's voltage with no load on it, then you would measure 30 volts. But if there's any load at all, you won't get 30 volts, and we'll show you that. we're going to make an equivalent circuit now. Let me read and see what they wanted us to do. They wanted us to find the equivalent resistance of the circuit. Yeah, that's what we're going to do. And the current out of the battery, the current through each resistor, potential drop across each resistor, power of each resistor, power supplied by the battery. There's only one battery. I don't know why they said batteries. But see, we're going to make a equivalent circuit. And here it is. And this, we haven't changed that any. That's still 1 ohms, 30 volts. But what we're going to change is we're going to make an equivalent resistance there and there. Oops, I forgot this one. Now to find this one here, you know the drill, they're in parallel, so you have to go 1/9. 1/9 plus 1/18 equals 1 over the resistance. Well, if you do that, I think you get I think this R turns out to be 6 ohms. Put this in your calculator and see if I'm right. I could be wrong on that. Take 1/9 plus 1/18, and then you have to take the reciprocal of it. Yeah, I got that right. Does anybody need help with that? If you do, just speak up. Now on this one here, you do the same thing here. That's 1/10 plus 1/10. That's going to give you 1/5. So see, this is 5 ohms. Come on now. Let me get out another pencil here. This one's just about wore out. We'll try this one. Okay, now this is an equivalent circuit to this. They're what you call, yeah, look at that. That writes better. They're equivalent circuits. Now we're going to do one more. We're going to do one more equivalent circuit. So you got your 30 volts. Ooh, that writes better. And you just add these up. 6 and 5 make 11, and 8 make 19, and 1 makes 20. Hey, look, we've got an equivalent circuit here. You know what I did? I just added those because they're in series. When they're in series, you just add them. This circuit is equivalent to this circuit. This circuit is equivalent to this circuit. We simplified it. Now, some people, instead of calling this equivalent circuits, they call it simplification. We simplified things. And see, I can get the current now. Because if you have 30 volts and 20 ohms, you know how it works. V equals IR. Ohm's law for resistors. And if V is 30 and the resistance is 20, I'm getting 1.5. I'm getting 1.5 amps. I'll be glad to write that down if anybody needs me to. Just speak up.
I have a quick
See
question.
if anybody else has shown up here.
I have a quick question.
Yeah, go ahead, please.
wasn't there another one where it's opposite? Was that the capacitance or something like that? Where when it's in
Yes,
series, it's
exactly.
opposite? All right,
Yeah.
cool.
See, when capacitors are in series, that's
Capacitor.
Zach. That's Zach talking to me, right, Zach?
Yep.
When capacitors are in series, you go 1 over C1 plus 1 over C2 plus 1 over C3 equals 1 over the total.
Right.
But see, with resistors, when you have resistors in series, you just add them up. You go 6 plus 5 plus 8 plus 1 makes 20. But I'm glad you mentioned that. But you're okay, right, Zach?
Yep. Yep.
Yep, good. Okay. And Zach, you understand that you got 1.5 amperes going through here.
Yep.
Great. We've simplified. We've done equivalent circuits. And now what you do is you go backwards. We figured out that we have 1.5 amps coming out of the battery. And we can get the volts now. See, the volts is equal to the current times the resistance. Well, 1.5 times 6, I can do that in my head. That's 9 volts. I like my volts in red. So we're going to put 9 volts right here. 9 volts. There we go. Now we got 1.5 amps and 5 ohms. V equals IR. So we can get the voltage there. 1.5 times 5. I can do that in my head. I believe it's 7.5. So what we have here is 7.5 volts. Now we got 8 ohms here. We have 1.5 amps coming through here. In series, the current is the same. And if you have 8 ohms and 1.5 amps, V equals IR, the current's 1.5, the resistance is 8, I get 12 volts. So you have 12 volts there. Now you have a 1 ohm resistance there, and you have 1.5 amps. V equals IR. The current's 1.5. The resistance is 1. I get 1.5 volts. But you got to understand that's internal to the battery. See, this is the battery. Now, what we've done is we started here and we did an equivalent circuit here and an equivalent circuit here, and now we went backwards. We went from here to here, and you understand all that. And now we're going to go from here to here, and we're going to fill in all the details. Well, see, you got 9 volts across both of these. They're in parallel. When you're in parallel, the voltages are the same. We probably ought to write that someplace. Yeah, here's some room up here. Parallel volts are the same. I didn't spell parallel right. I think that's right. Did that come out? Yeah, you can, maybe you can see that. Now, when you're in series, the current is the same. See, these are in series, so the current is 1.5 amp in this one. It's 1.5 amps in this one. It's 1.5 amps in that one. It's 1.5 amps in that one. The current is the same. Ah, but these are parallel. The voltage is the same, and we know what it is. It's 9 volts. I like my voltage in red, so I'm going to put 9 volts here. And the volts here is 7.5 volts. And the volts here is 12 volts. And the voltage here is 1.5 volts. Now, the battery itself is no longer has 30 volts across it. It did before when we didn't have any connection and no current through it. But see, because you've got 1.5 volts here, that battery is going to have 28.5. From positive to negative, it's going to have 28.5. It won't be 30. It'll be 28.5. Now here's why. You're going to have to get used to this. Whenever you have a resistor, let me make some room down here. If you have current through the resistor like this, resistors always have a positive voltage here and a negative voltage here. The voltage is smaller because you've got more energy. See, voltage is energy. Voltage is energy per charge. It's joules per coulomb. And you have more energy here and less energy here. Where did the energy go? Well, it went to heating up the resistor. See, when you have current running through a resistor, they can get hot. The resistor can get hot. Well, that's energy. You're using energy. And so you have to have more energy here and less energy here. The voltage is higher here. It's always this way. Now, batteries are different. If your battery is like this and your current is like that, that battery is providing energy. You've got your positive here and negative here. That's the opposite of this. That's the way batteries normally operate. But if they operate like this, batteries can do that too. But see, this here is called charging. Did you know you can charge your battery? This is charging when your friend brings the, what do they call those where you connect your charging cables, your battery cables. Your friend gets his or her battery cables out of his trunk, connects up your battery. The current goes like this, and you're charging the battery. You're charging your battery. But this is the normal condition of when you're using a battery. Like if you have a transistor radio, the current goes like that in your battery. And that's what's happening here. See, the current's going this way. There's your current. It's like this. It's not being charged. It's being used. Well, I hope that made sense. Now let's get the current in each one of these. Well, guys, if you know the volts and you know the ohms, V equals IR, I can get the current through here. It's going to be 1 amp. Because 1 amp times 9 volts, or times 9 ohms gives you 9 volts. Now this one here is going to be 0.5 amps. You got 9 volts. Look, V equals IR. If the volts is 9, the current has to be 0.5 times 18. 0.5 times 18 will give you 9. Notice you get a 1 amp and a half amp. That's 1.5 amps. That's what we decided earlier. You have 1.5 amperes coming here, but they split. The current splits. See, when you're in parallel, the voltage is the same, but the currents are different. Because 1 amp went this way, the half amp went this way. The way it works is most of the current goes where the resistance is smaller. See, 9 is smaller than 18, so most of the current went this way. Now here, since these are both the same, the currents will be the same, and they will be 0.75 amperes here and 0.75 amperes here. And then they'll come back together and make 1.5 amps coming out here, going through that 8 ohm resistor, gives you 12 volts. And you have 1.5 amps here, going through a 1 ohm resistor, gives you 1.5 volts. And we're done with all of the currents and the voltages. We've got the current through each component. We've got the voltage on each component, but we don't have the power. And we solve this using what they call equivalent circuits, or some people call it simplification. Now we're going to do the power on each component. But before we do that, do you have any questions on it? Anybody have a question on what we've done so far? What we've done is problem 1069. It's in your book. It's on page 491. They even have answers in the back. We could look back there and see if we got any numbers like they said. Let me look at their answers. We'll see how we did.
I got a question.
Yeah, go ahead.
I understand how all this works out mathematically, but
Yeah.
like if you were to take a voltmeter and test, measure voltage at the resistor.
Yes.
Where would you measure it on the coming into the resistor or the
Let me show you, Zach. You take your voltmeter. Now, a voltmeter has it has a red lead and a black lead. You put your red lead right here. Here's your red lead. You put it right there. And your black lead, you put it right there. And then, here's your voltmeter. I don't know, I'll put a little arrow in there.
So when you say you got 7.5 volts at the resistor, that means it's across the potential across the resistor.
Yeah, 7.5 volts across the resistor.
Okay.
Yeah, that's another topic for tonight, is voltmeters. It's next. We'll talk about voltmeters and amp meters here in just a minute, but thanks for mentioning it. But that's how you would connect it to measure the voltage. I think we've measured voltage already. Oh yeah, haven't we done some labs with some voltages? Seems like we have.
Yeah, we did some voltages.
Yeah, we've measured that. But by the way, I put your new lab on content. It looks like this. There's the front page, and then the back page is like that. We'll be doing that Thursday night, and this is on content. Just go to your course there and click on content. If you have a printer, you can print that off, but I'll bring some copies to lab on Thursday night for those of you that don't have a printer. Now, let's see, where were we? I was going to show you the power on every compound. Oh, I was going to look at the answers and see how we did. This was problem 1069. And in the back, problem 1069, they said the equivalent resistance is 20 ohms. Well, that's what we said. Look, hey, look, you see that 20 ohms? That's in the answer book. We got that right. Now let me keep reading. They said one of the currents is 1.5 amps and another current is 1 amps. Well, we got that. Look, wait a minute. Yeah, there's 1.5 amps. And they said that was one of the currents. Then they said there's a 1 amp and a 1/2 amp. Look at here, it splits a 1 amp, a 1/2 amp. That's exactly what the answer book says. And then they said there's 0.75 amps and 0.75 amps. Hey, that's us. Look, 0.75 amps, 0.75 amps. We got that right. And then they said something about 1.5 amps. Well, I think that's just here, coming out of here. You go back to 1.5 amps. So we got everything they got, but then they go on and do the powers. Let's do the powers before I won't peek at the answers there. I just need a little room. Now, you know how we were able to do this. We use simplification. I'm just going to erase all that. We don't need it anymore. But we needed it to solve. But now we're going to find the powers. Now there's 3 equations to find power. You can go IV, or you can go I squared R. Oops. Or you can go V squared over R. They all give you the same thing. But let's do that. I wonder if I could maybe put the power in. I've got a green here. Let's use it. Okay, if you wanted the power in this resistor here, I don't care which equation you use. If you use the first one, you know the volts and you know the amps. I'm getting 4.5 watts. Let me write that down. This is 4.5 watts. Does that show up in green? Well, kind of. Not very good. 4.5 watts. Let's do this one. Well, now you can use that again. You can go 1 amp times 9 volts. That's 9 watts. So I don't have much room to write there, but I'll just fudge it and stick it in here someplace. We got 9 watts there on that one. Now let's do this one. I'm using this one all the time, but you could have used these. You'll get the same answer. If you do this one, you'll have, you do it. I'm having all the fun here. You do. Find the power. Of course, it'll be the same because they have the same volts and the same amps. Find the power in those resistors there. Go for it. I'm going to do it. You do it. Find the power. Right now, we're trying to find the power in this 10 ohm resistor here. Of course, it'll be the same power in that 10 ohm resistor because they have the same current and the same voltage. But let me go to one of my students here. Gee, we have a small class. We only got 3 people showed up tonight so far, but they can watch it on YouTube when my daughter puts it on YouTube. Sometimes it takes her a couple of days. She's a busy girl. How about it, Nicholas? Have you got the Have you got the power in this 10 ohm resistor right now?
Yeah, 5.625 watts.
That's what I got. I got 5.625 watts. Same thing here. This is 5.625 watts. Same one. Now let me just show you. The way I did that was I went the current, which is 0.75 amps, times the volts, which is 7.5 volts. And when I multiplied those, I got 5.625 watts. But we could have done it this way. Let's try it. What is the current? It's 0.75 amps. And so you could square that times 10 ohms. Try that. You'll discover it's the same. Or you could have done this here. You get the same answer. Let's do it that way. Take your 10 volts. No. It's not right. Take your 7.5 volts. Square it and divide by your 10 ohms. And you'll get 5.625 watts. So all three of those are perfectly good. Now let's get this one. Let's get the power on that one. Okay, now how do you do that? Well, I think it's 18 watts, isn't it? 18 watts on that one. Now let me double check. Yep, it's 18 watts. Now let's get this one here. Let's get the power on this one. Well, that's well, it's 1.5 squared. You know what this is? It's 2.25 watts. 2.25 watts. All right, now we've got all of our watts. We haven't done the watts on the battery though. We can do that. Now on a battery, you can't use these two. You see these two equations here? You can't use those two, but you can use this current times the voltage. Now the current is 1.5 amps and the voltage is 30 volts. That makes 45 watts. You got 45 watts. Now let me show you. We could go and look at the answers in the back, but I bet those are right. But I'll show you a way you can check your work. You see, there's power provided. Power provided, and there's power used. Now, there's only one thing providing power, and that's the battery. The resistors don't provide any power. Resistors use power. So the power being provided is 45 watts. Now let's list all the power that's being used. Well, you got 9 watts, 4.5 watts, 5.625 watts, 5.625 watts, 18 watts, and 2.25 watts. Now, if you add all those up, it's got to equal the power provided. Get your calculators and add all that up, and let's see what we get. I'm going to add these up now. Well, I added all those up, and guess what I got? I got 45 watt total power used. Total power provided is 45 watts, and the total power used is 45 watts. This is a way you can check your work. If you total up all those powers, and they add up to the power provided, you must have done something right. Let's see what the answer book says. This was problem 1069. And they said, here's some of the things they got. They got a 2.25 watts. Yeah, look, there's a 2.25 watts. And they got a 9 watts and a 4.5 watts. Oh, look, there's a 9 watt and 4.5 watts. They got a 5.625 and a 5.625. Look, that's what we got. And they got an 18 watts. Hey, we got the same answers they got. And how did we do it? We used simplification, or another term is called equivalent circuits. Okay. Do you have any questions on that? Well, I guess you're okay. Let's talk for just a minute about ammeters and voltmeters. Now, they have that in your book here. Let me show you where it is. And you've actually connected ammeters and voltmeters in the lab. We've done that. We've connected ammeters. Here we go. This is on page 470 and 471. And here's what you have to remember. I need a little room here. I'm just going to erase all this if you're happy. Speak up if you want to ask me anything. Okay, nobody spoke up. All right. Now, the way it works is ammeters are connected in series. If you want to find the current, say right here, remember we had a 1.5 amperes going through here. What you would do is you would break the circuit. You have to break the circuit. That's the bad thing about ammeters. You have to break the circuit. And you put the ammeter in the circuit and it'll read your current. It has to go in series. Now, voltmeters, I like them better. You don't have to break the circuit. They work in parallel. And like we did, we put this voltmeter, we put the red lead here and the black lead there, and it would give you 7.5 volts. That's what this thing would read, that voltmeter, 7.5 volts. They're placed in parallel. You don't have to break the circuit. So actually, when people are using voltmeters, what they'll do is these things usually have what is known as a ground. The symbol for it is a thing like this. They'll put the black lead right there on the ground, and then they'll go and they'll measure what the volts are everywhere. And here's what you would get. If your voltmeter is on this ground, that's what we're going to call 0 volts. And then you connected your red lead to here, it would read 12 volts. Now, if you connected your red lead to here, it would read 19.5 volts. Do you understand it? You got 12 volts here, 7.5 volts here. That's a total of 19.5 volts, all relative to the ground. Now, if you connected your hot lead here, up here, like that, you've got your ground lead here, put your hot lead there. Now, what would the voltmeter read there? You tell me. I'll pick on somebody here, one of my best students here. Phoebe. Well, no, ma'am, she's in her car. I don't want to call on her. Phoebe, are you still?
I'm still driving. I'm sorry.
Yeah, that's why. You just listen, I guess. We'll pick on Zach. Zach, if you put your black lead here,
I got 28.5.
What do you get for your volts there, Zach?
28.5.
Now let me do it. Let's see. You have 12. 7.5 makes 19.5. Another 9. 28.5. Good going, Zach. You would measure 28.5 there. And you know what that is? That's the voltage across your battery. Remember that battery. Here's your battery. It has this internal resistance of 1 ohm, and it's got what they call 30 volts EMF. And if you measured your voltmeter across that with no circuit involved, it would measure 30 volts because there's 0 volts now on the resistor. There's no current. See, V equals IR. If the current is 0, then the volts will be 0. And if you took your voltmeter with no current in your battery, you'd get 30 volts. That's what they mean by the EMF. But see, in this case here, we've got current in our resistor. We've got a current of 1 ohm. And so that makes a voltage of 1.5 volts. Now, I want you to notice that these are opposing. Plus, minus, minus, plus. They're not helping each other. They're, in a way, fighting each other. So what you get with a voltmeter across this is what Zach said. I think it was 28.5. Yeah, that's it. You get 28.5 volts if you connect across the battery. And let me repeat about these resistors. Students get confused about this. If you have current going this way, the voltage on this end will be plus, minus, like that. If you have current going this way, the voltage will be plus, minus, like that. Now, if you have a resistor like this, and the current is going that way, see the current's going down, this is plus, minus. Just memorize this, okay? Memorize it. If it's like this, if the current's going up, this is plus, minus. Just memorize the way that works. Now the way I remember it, it's a little bit like going shopping. When you go shopping and there's a big crowd, it makes me tired because I've got to fight my way through the crowd and I have less energy. See, if I'm going this way, and there's a crowd, and I have to work around all these people. Just looking at them makes me tired. And when I get to here, I've got less energy than before I started. But see, if I'm going this way and I'm fighting my way through a crowd like this, I've got more energy here and less energy here. Same as here. If I'm going this way through a crowd of a whole bunch of people, I've got more energy when I started and less energy when I get through. Maybe that'll help you remember it. But batteries are different and capacitors are different. Here, let me show you with the capacitors. I need some room here. I think we're through with that, unless you have a question. Anybody have a comment or question? Okay, well, let me show you about capacitors then. Capacitors are kind of like batteries. You can have current going like this, in which case this will be plus and minus. Or you can have current, you can have plus minus on a capacitor like that and have current going this way. See, now what this capacitor is doing is it's charging. The pluses are coming in here and they're filling up this positive plate here. And when they do that, they make this plate negative because they repel the positives, and the positives go that way. And current is always the motion of positive charge. But here, you've got positive charges coming in this way, and this is called discharging. The capacitor is discharging, and we did an experiment like that. We had a discharging capacitor, and the current, the positive charges are moving this way. They're being repelled, and they're going through a circuit, and then the positive charges are coming back in here. And eventually, that capacitor will have a zero charge. It will be completely discharged until somebody charges it up again. This is charging, this is discharging. Capacitors can go either way. Resistors can't, though. If you have a resistor like this one here, if this is plus and this is minus, the current's going that way. It can't go the other way, I'm sorry. But see, with a capacitor, you can have plus and minus, and you can have the current going that way. It's called discharging. Now with a battery, it's the same kind of thing here. Let's do that. This is your positive end on your battery. And this is your negative end. I think I did that the wrong way. Let's do it this way. Your current's going like this. This is your positive end. This is your negative end of your battery. Current's doing that. We don't say charging and discharging. What we say, this is the normal operation of your battery. The pluses leave the positive plate, they're repelled, and they go that way. But now if your battery is like this, you can have the current going that way. Hope we're not getting terribly confused here. But see, this is called charging. You know what? It's just like the capacitor. See, this is a capacitor that's charging. This is a battery that's charging. Now, this is a capacitor that's discharging, but you don't talk about batteries discharging. They're just functioning like batteries normally would in a circuit. That's the way the current has to go in a battery that you're using to power a circuit. So we're not confused. Any comments or questions on any of that wonderful stuff that we just studied? Well, okay. Let's do a couple of problems, and then we'll have some more wonderful theory. I'm going to erase all this if you're happy. Okay, we talked about voltmeters and ammeters a little bit. Simplification. Equivalent circuits. We haven't got the Kirchhoff's laws yet, but we will. We're getting there. That's what the lab is about. And I put it on content so you can look it up and study it. And we still just have our 3 wonderful students that stuck with me tonight. And the others, maybe they can watch it on YouTube. What I want to do right now is problem 1025. In your book. Help me find it. 1025. Okay, I'm trying to find 1025. Yeah, there it is. I found it. We have a 12-volt EMF automobile battery. And I explained what that means. The 12 volts EMF. See, that would be the voltage if your battery didn't have any current, if it wasn't connected to anything. If you just put a voltmeter on it, that's what it would say. But it has a terminal voltage of 16 volts when it's being charged by a current of 10 amps. Well, let's draw that. Here we go. We have a 12 volt battery. But see, it's being charged. You know what that means? That means you have a current coming in here. Current is always the motion of positive charges. And you're putting positive charges and you're increasing the number of positive charges. And of course that repels the positive charges and they go this way. But now this battery has an internal resistance. And if you read the problem, we're doing problem 1025. It has a terminal voltage of 16 volts. Now what they mean is, see, you don't get to actually see this internal resistance. It's internal. You don't see that. It's in there, but you don't see it. But when you have this current of 10 amps, there's 10 amperes coming in, then the voltage across the whole thing is 16 volts. Now, the way this current's going, the current's going this way, we know that has to be plus minus. This is plus minus, that's plus minus. Those add up. You know what you got right here? You have to have 4 volts. The 4 volts and the 12 volts add up to 16 volts. They call that the terminal voltage. You've seen batteries, you know what they have. Like on these 9-volt batteries, they have a positive and a negative, and it says 9 volts. That's what you have if it's not connected to anything. But see, what we're doing is we're charging this battery. That's supposed to be a minus. There we go. We're charging it. They call that the terminal voltage. Now, if you're discharging, let's say you connected this thing up to a load. We'll put a load right here. You're not going to get 9 volts. I'm sorry. The internal resistance uses up some of your voltage, and you might get 7 volts. It's still a 9-volt battery, but because you have current going through it, you don't get 9 volts anymore. It's kind of like when you go out to your car and you turn on the lights. You pull that switch and the lights come on nice and bright. And then you take your key and you hit your starter motor. Brum, brum. When you do that, the lights kind of dim a little bit. I need to ask one of you if you know what I'm talking about. Let's go to my friend Nicholas. Nicholas, have you ever experienced this? You go to your car, turn on your lights, and they're nice and bright. Your engine isn't on or anything. You just turn your lights on. Then when you start your starter, boom, boom, the lights dim. Have that ever happened to you, Nicholas?
Yeah, every time.
Yeah, because what happens is your voltage goes down. It was a 12 volt car battery, but once you started that ignition and you got your starter motor, it uses up some of the power, and you don't have 12 volts anymore. It goes down. But see, we're doing just the opposite here. We're charging this thing. This was a 12 volt battery, but now it measures 16 volts, but we're charging it. And we have 4 volts across the internal resistance. Now let me see.
So what happens to volts if it's not in parallel?
Say that again, please.
What happens to the volts if they're not in parallel?
Well, now these are not in parallel. These are in series. I don't have anything in parallel. You lost me on that, Zach. What's in parallel?
Well, no, it wasn't about this being in parallel. You just said before that parallel volts are the same.
Yeah.
Okay,
The voltage is the same in parallel.
So because it's not now, we had to add up.
Well, we don't have anything in parallel. If we did, the voltage would be the same.
Okay, now I understand that.
Yeah, you got me confused now. Don't do that. You're messing with my mind. Okay. Let's answer their question. They said, what is the battery's internal resistance? Well, here's how you do this. V equals IR. The voltage on this internal resistance is 4 volts. The current through it is 10 amperes. So you tell me, what's the resistance? Somebody go ahead and tell me, what is the resistance? This internal resistor. I should use a little R there. I'm waiting.
0.4?
Yeah, there you go. It's 0.4 ohms. Good going. We have an internal resistance of 0.4 ohms. Now let's see what else they want. what power is dissipated inside the battery? Well, we can do that. We have three lovely equations. They go like this. My favorite is this one here. This one. The current is 10 amps. Square it. Multiply by 0.4. And what do you get? What do you get for the power? Their fancy word is dissipated. What power is dissipated inside the battery? You tell me.
40 watts.
I get 40 watts. That's what I get. You got 40 watts. Now let's keep reading. At what rate in Celsius per minute will the temperature increase? They're talking about the battery. If its mass is 20 kilograms, gosh, that's a big battery. You know what? That's about 42-pound battery. I don't think a car battery weighs that much, does it? How much does a car battery weigh?
Probably not quite that much.
No, they're heavy. They're heavy,
Oh,
but I don't
heavy.
think they're 42 pounds. But here's the thing. We're charging this battery, and it does make it get hotter. Well, this 40 watts has to go someplace. And what it does is it goes to heat. It makes the battery hotter. Now, they said the specific heat of this battery is, let me write this down someplace. Do I have room down here? Maybe. They said it's, I need to acquaint you with this equation. The way it works is this, if I can remember how to do this. Energy, I'll use E for energy. The energy is equal to the mass times the specific heat times the change in temperature. Yeah. And the thing is, they want to know at what rate in Celsius per minute. So they're dividing by a minute. They want to know the energy per minute. Well, a minute is what, 60 seconds? You'd have to divide this by 60 seconds. At what rate well, is that right? The energy in 60 seconds should equal, that should be the power. Energy per time is power. And at what rate will its temperature increase if its mass is, I don't know, guys, we'll figure this out. They said the mass is 20 kilograms. And they said the specific heat is it's kind of complicated, 0.300 kilocalories per kilogram per degree Celsius. And I think they want the temperature. We don't know what the temperature is. I think this is what they want. They want the change in temperature for 60 seconds for a minute. At what rate in Celsius per minute will the temperature increase if the mass is in, okay, assuming, all right. Now, how are we doing on all this? Sure, but I'm thinking about it. Now, there's a problem here. We're not used to kilocalories. We're going to have to do a little conversion from kilocalories to joules. So let me look that up in the back. In the back of your book, if you snoop around, they've got a whole bunch of nice tables back here of kilocalories, pressure, mass, time, seconds. I need kilocalories. Let me keep looking back here. I'm in the back of your book snooping around. You know they have to have energy back here someplace. Yeah, here we go. A calorie is, here we go. 1 calorie is equal to 4.186 joules. Now what they've got is a kilocalorie. See that kilocalorie? A kilocalorie would be 4,186 joules. These are all units, so probably should put them in brackets like that. So what I'm going to have to do is I'm going to have to multiply this by 4,186 joules is a kilocalorie. That'll get rid of my kilocalories and give me joules. I'm confused about this this business here about the 60 seconds though. See, if you look at the units here, you're going to get joules. This will be energy in joules. What do they use in this book for energy? Is it U? I think it's U. The energy in joules is given by this equation here. This is called the specific heat. And see, we've converted it to joules. And this will give you the time. We don't know what the time is. But I tell you what we do know. We know we can find the power used in that little resistor. And you know the equation for that, P equals, here's my favorite, I squared R. We know the current, it's 10 amps. And R is 0.4 ohms. We did this before, I just got mixed up. And yeah, we get 40 watts, that's it. So if you wanted the energy, you'd have to take 40 watts times the 60 seconds. See, a watt is a joule per second. And if you multiply by seconds, you'll get joules. So if you want to find the energy used in 60 seconds, we know this is a 40 watt internal resistor. We got a nice equation now, guys. It's kind of long and messy, but we all have calculators. And looky here, this comes out to be joules. This comes out to be joules, because this is going to be Celsius. That'll cancel, the kilograms cancel, and we can find the change in temperature in 60 seconds. I'm going to shut up and I'm going to let you solve this equation. On your mark, get set, go. And we'll see how much temperature changes. And I'm going to call on one of my excellent students. We'll call on one of my excellent students here. There's only 3 of you, and you're all excellent. Nicholas, I'll pick on you. Nicholas, what'd you get for the change in temperature?
Well, it wants it in degrees per minute, right?
Yeah, well, this is just going to be degrees, but we did it for a minute. What'd you come up with?
Well, I got 0.0 or like 0.10 degrees per minute.
You got what I got, Nicholas, only I got 0.0955, a bunch of fives. And you just rounded off, didn't you?
Yeah.
That's degrees Celsius. Now, that's the change in temperature for 1 minute. It's not much. In 2 minutes, you'd have to double that. It would take you about 10 minutes to change the temperature 1 degree. It's not heating up much, is it?
I got
Now
9.55 times 10 to the negative fifth.
I'm getting 0.0955, and you're getting what?
9.55 times 10 to the negative fifth.
Okay, do it over again. That's a 0.3 there.
Oh, it's a 0.3. I got 300. Okay.
Now that's a 0.3, and you'll get that. Now, if you look at the answer, 1025, help me look up the answer. 1025, they said .0956 degrees Celsius per minute. They got what we got. In 1 minute, that's how much it heats up. So we got what they got. We did great. So that battery is heating up. In about 10 minutes, it'll be 1 degree hotter than it started. And in 20 minutes, it'll be 2 degrees hotter than it started. So it doesn't really get that hot, does it? You're charging that battery. It's important that you know how to manipulate these units. See that kilograms? They cancel. You see these degrees Celsius? That's what this is in. That's in degrees Celsius. They cancel. Do you see those kilocalories? They cancel. And what you're left with is joules on the right. And what a watt is a joule per second. And see those seconds? They cancel. So you have joules on the left, joules on the right. I hope you can learn to manipulate units without getting too confused. Now let me talk to you about calories and kilocalories for just a minute. I need some room here. I think we successfully did that problem. You've all heard of a calorie. You know what a calorie is? It's the amount of heat energy that is required to heat up 1 gram of water 1 degree Celsius. If you have 1 gram of water, which isn't much, 1 gram is just a little about a spoonful, and you want to heat it up 1 degree Celsius. They used to call it centigrade when I was in school many years ago. It requires 1 calorie to heat up 1 gram of water 1 degree Celsius. Now, I'll tell you what a kilocalorie is. A kilocalorie is the amount of heat energy you need to heat up 1 kilogram of water 1 degree Celsius. That's the difference. Now, they oftentimes capitalize the calorie. There's a little calorie, a little c like that. That's just the regular calorie. And there's a big C like that. That's really a kilocalorie. Now, when you go buy one of those candy bars at the checkout line at Walmart, and you read the back of the candy bar, it tells you the calories. Those are capital C's. Those are really kilocalories. When you go on a diet, and there's so many calories in this bowl of mashed potatoes or whatever, those are kilocalories. So I thought you'd like to know that. Well, that was fun. And we did some problems there in your book. Let's see what's next here. Well, I think what's next is we should take a little 10-minute break. That's what we're going to do. I might go scrounge around in the refrigerator and see if I can find something. But we're going to be back, well, definitely by 7. That would give us almost 14 minutes breaks. That's too big a break. A little before 7, I'll be back for more fun. And the topic then is going to be Kirchhoff's laws. We're going to study Kirchhoff's laws. Go stretch for a minute. We'll be back. Go stretch. Minus 10. No, you have to subtract minus means minus. Son las 7 minus 10.
Buns, outside, where'd you go?
Well, it's time to get started again. And let's make a little room to operate here. The topic right now is Kirchhoff's laws. Tuesday, September 29th. Tomorrow's the last day of September. And we're in Physics 2. And our topic is Kirchhoff's laws. He has two laws. He has his current law, KCL. That's Kirchhoff's current law. And he has KVL. That's Kirchhoff's voltage law. Now these laws, these Kirchhoff's laws, you can use them on a lot of different circuits. I won't say on every circuit, but they'll do thousands of different circuits. But see, the method we used earlier tonight, let's see if I've still got some customers here. Yes, we still have our devoted 3 students, see, we used a different method. We used what they call equivalent circuits. Equivalent circuits. And another name for that was the simplification. The thing is, that method doesn't always work. The Kirchhoff methods on these circuits that we study, it always works. But the equivalent circuit method, they don't always work. Let's do an example, shall we? Now this is on, well, maybe I should tell you what these laws are. Now the current law, what that says is if you have an intersection, like, well, if you have an intersection, you know, here we go. This could be maybe Memorial and I don't know, 41st. What do you think? Memorial and 41st. And if 3 cars come into this intersection and 2 cars come into this intersection and 1 car comes in this intersection, you can figure out if that's all day long. That's silly. Let's talk about maybe a 5-second period of time. In those 5 seconds, 3 cars enter here, 1 enters here, and 2 enter there. Well, then what do you have going out that way? Well, it would be that's 41st Street. If you have 1 and 2 and 3, well, you'd have six cars going out that way. That's all Kirchhoff's current law says, is that they have to add up. Now you might have 3 coming in here, 2 coming in here, and let's say you had 5 going out here. Well, what do you got here? Well, it'd be 0, wouldn't it? You wouldn't have any cars at all there because 2 and 3 make 5, and if they all go this way, there aren't any going that way. But that's all it is. And the way you'd write it is Kirchhoff's current law is written like this. The sum of all the currents is equal to 0 at an intersection. Now it might just be a T. You know, you might have cars coming in here, like 2 cars coming in here, or these are currents. Like if you have 2 amps coming this way and 3 amps coming this way, then does it make sense that you would have to have 5 amps of current going that way? It's that simple. That's Kirchhoff's current law.
Yes, that makes sense.
Yeah, it makes sense to me. Now the voltage law is equally easy, but what it says is the sum of all the voltages around a loop is 0. And we'll show you that in our example here in a minute. But here we'll do a loop. Suppose you had your 9-volt battery, and you had 10 ohms and 20 ohms. Well, you could figure your current. I did that in my head, and I probably did it wrong, but I'm getting 0.3 amps. I wonder if that's right. If you take 9 volts and divide by 30 ohms, Do you get 0.3 amps? Do you? Let's see. Let me get my calculator out. 9 divided by 30. Yeah, that's right. Now let's get the voltages. I like voltages in red. V equals IR, so this would be 3 volts. And V equals IR. 0.3 amps times 20 ohms is 6 volts. There you go. Now here's what Kirchhoff says about going around this loop. We'll call this a loop. Around and around you go. Well, going from here to here is plus 9 volts. Going from here to here, remember how resistors work. If the current's going this way, they have to go plus minus. So that's a minus 3 volts going from positive to negative. And then this one, see, it goes from positive to negative. If the current's going this way, you have to have a higher voltages, more energy. Remember my going to the shopping with the crowds? I got more energy when I try to get through that crowd and less when I get through it. But see, that's minus 6 volts equals 0. That's what he says. The sum of the voltage changes when you go around a loop is 0. Now you can always use Kirchhoff's laws, but you can't always use the simplification or the equivalent circuits. Now we're gonna do a problem now. This is on page 461 in your book, and we're going to do that. And then Thursday night, you're going to be doing a couple of circuits. And you're going to be measuring currents and voltages. Actually, I think you'll measure voltages, and you can figure the currents from V equals IR. So if you know the resistances and you know the voltages, you can get the currents. Okay, now this is problem, it's on page 461. Yeah, there it is. Here, let me erase all this and we'll put our circuit here and we'll solve it. But this problem cannot be solved with simplification. It's on this page. It's kind of down in the corner, the lower left-hand corner. And here's what we've got. Now this is 24 volts. These are the EMFs. Remember what that is. That's 29 volts. 4 ohms, 3 ohms, 3 ohms, and 3 ohms. This circuit can be found in your book on page 461. Yeah, and we're going to solve it using Kirchhoff's laws. Great. Okay, well, the first thing you have to do, step number 1, of course, you have to draw your circuit. You got to draw your circuit. So I did that. Step number 2, and you have to label it. I did that. See, I put 24 volts and 29 volts, 4 ohms, 3 ohms, etc. Did I get everything correct? Yeah, I think I did. Yeah, it's all correct. Did I get these polarities right? Yeah, I think I did. Draw and label it. Draw and label your circuit. We did that. But now the next thing you do is you do your polarities. And I like those in red. Well, no, we're going to do the volts in red, aren't we? Never mind. But this is your next step. Is that how you spell polarities? I believe it is. Yeah, that's right. No. I'm rusty at this. You can't do the polarities until you assign currents. You have to assign currents. That's your second step. Then we will assign polarities. Okay, now we have to figure out the way the currents are going to go. Well, kind of hard to say. The thing is, if you screw up on this and you get this going the wrong way, the algebra will give you a negative answer, and that just means your current's going the opposite way. It'll work out. Maybe we could work it that way. But the way batteries normally operate is the positives leave the positive terminal and go that way. So we'll have a current going this way. And here, this is the positive terminal. And the way batteries work is the current will be going that way. Why don't we give these names? Why don't we call this I1 and I2? Those are nice names. And see, of course, I1 is going here, and I2 is going here. And you know what this is according to Kirchhoff's current law? This would be I1 plus I2. So we have assigned currents. Now we're going to assign polarities.
I just have a question.
Yes, go ahead.
How did you know how to do that? I know that sounds dumb, but like, how did you know which one you wanted to set up which way? Does it matter?
Well, with a battery, they normally operate this way. The current leaves the positive. See, current is the motion of positive charge, and they want to repel that positive terminal and go that way. See this positive terminal? The positive charges will get the heck out of Dodge. They're going this way. Did that answer your question?
How did you know which side of that you wanted to assign to be positive and which side you wanted to assign to be negative?
Oh, okay. Now on a battery, thank you for asking. Sometimes they'll draw batteries like this, but the big thick side is the plus side, and the little side, that's the negative side.
Okay, that makes sense.
Yeah, thank you for asking though. Yeah, thanks. Good going. And you can see if we label this I1 and I2, and if that's I2, well then that's I2. And if that's I1, that's I1. And how about when you add those together, I1 plus I2? A little Southern talk. Y'all happy with that? Y'all happy with that so far?
Yep.
Okay, well,
Yes.
good deal. Yay, we're happy with that. Good, excellent. Okay, now that was step 2 and 3, and now step 4. Step 4. Now we snuck in a KCL. I kind of snuck that in, but see now we're going to do the KCL and the KVL. That's step 4. I already did the KCL. If you want to write the KCL separate, what that is I1 plus I2 something people would call this, say, I3. I1 plus I2 is I3. That's your KCL. But we don't need to have another unknown. Let's just call this I1 plus I2. So we did our KCL, and now how about our KVL? By the way, if you try to use simplification, you can try all night long, but this circuit can't be done with simplification. Sorry. Just can't. But you can do it with the KVL. Kirchhoff always works. And here's what you do. You just start at any place you want and go around a loop. There's two loops here. Or you could consider one great big loop. But you only need two equations because there's two unknowns. But traditionally, I'll just start here, and I'll go around this loop here. And here goes. We're going to write it. This is step 5. We're going to write, wait a minute, I didn't do my polarities. Is that how you spell polarities? Is it OR? Is polarities P? Is it POLOR or POLAR?
It's AR.
I think it is. I think it is. I think I got it right. I didn't do them. We got to do them. Now, guys, if the current's going this way, that's got to be plus and minus. If the current's going this way, that's got to be plus and minus. If the current's going this way, that's got to be plus and minus. Okay? Wait a minute. There's one more. If the current's going this way, that's got to be plus and minus. And now we're going to write our KVL equations. Here we go. Well, that's the method. And then what I'm going to erase all this. I need the room. The next step is just you do your math. There's going to be some algebra involved, but we'll be all right. And then the last step is to check your work, see if it makes sense. We're going to do all that. Okay, here comes the KVL equations now. I'm going to start here, and I'm going to go minus 3I1. See, that's the voltage. Voltage, V equals IR. V equals IR, and the current is I1, and the R is 3, so we got minus 3I1. And then we're going to go minus 3I1 plus I2. And then we're going to go plus 24 equals 0. The sum of the volts in the loop has to be 0. See, the reason for that is you've got so much energy. This is energy per charge is what it amounts to. If you're moving a single charge around this loop, you lose energy here, you lose energy here, you gain energy here, and it's supposed to add up to 0. Kind of makes sense. Okay, now we're going to do this loop here. I'm going to start here, and I'm just going to go around this loop. And so we have plus 3 times I1 plus I2. And then we have plus 3I2. And then we have plus 4I2. And then we have minus 29 equals 0. I just did a KVL around this loop here. And if you're happy with that, we're going to go on and finish it now. Here's our next step is the math. What I would do is combine these. You got minus 3 and minus 3. That's minus 6I1 and minus 3I2 equals minus 24. I put that 24 over on the right. Now let's do this one. We got 3I1, 3I2, 3I2, that makes 6I2, and 4I2, plus 10I2 equals 29. And now double check me, make sure that I haven't goofed up on that. Does that look right? Hey. Okay, now here comes the math part. Now the way I do this is, I think I would just double this. Double that, you get 6I1. Double this, you get 20I2. Double that, you get, I believe, 58. And I don't need this equation anymore. And then we have equals. You can add equals and get equals. See, when you add these, the 6I1 and the minus 6I1 go bye-bye, and you're left with 17I2 equals, is it 34? Did I do that right in my head? Negative 24 and a plus 58, is that right? Yeah, I think it is. So what's I2? Well, boy, Jove. I think I2 is 2 amps. What do you think? I2 is 2 amps. Okay, now take that 2 amps and plug it back in here, and we'll find I1. Now, if that's 2 amps, that's a minus 6. And that makes that minus 18. You know what I think we get? I think I1 is 3 amps, but let's double check it. It should work in this equation here. 6 times 3 is 18, plus 20 times 2 is 40. 18 and 40 make 58. Yeah, it works. We have got our answers. Now, the last step is called checking our work. We're going to check this, and we're going to put all our voltages in here. Now, here we go. If I2 is 2 amps, and you got 4 ohms, V equals IR, you know what? That's 8 volts, isn't it? V equals IR. If I2 is 2, and you got 4 ohms, 2 times 4 is 8 volts. Okay, well, let's do this one. I2 is 2, and that's 3. 2 times 3 is 6. You got 6 volts here. Does that show up red? Well, not very good. That's 6 volts. And this is 8 volts. Now let's do this one. I1 is 3 amps. 3 times 3, that's 9 volts. This here is 9 volts. Well, what's this one? Well, what's 2 amps plus 3 amps? That's 5 amps. 5 amps times 3 ohms, V equals IR. You know what? I think that's 15 volts. 15 volts. Now, do we have all the volts? I think we do. Let's check them. Do 15 and 9 add up to 24? Yeah, that worked. Do 8 and 6 add up to, wait a minute, no.
29, right?
We got 8, 6, and 15.
Right, and it goes to 29.
Yeah, now what is 8 plus 6 plus 15? Does that work? Yeah, 29. Yeah, that works. That works. Okay, hey, guys, we got all the currents. We got the current. See, there's 2 amps in here. There's 5 amps in here. And there's 3 amps in here.
So when you started it with the currents, you did minus because of how it was flowing from positive to negative?
Well, we know that the currents want to leave your battery and go that way. Is that what you're asking? Well, how did I know the current was going that way?
No, right here, what your first two equations, the minus 3i.
Yeah, this one here.
Yeah. So how you got the minus part and then how you got the plus
Oh,
part on the other.
the minus part. Well, see, what we're doing is we're going around this circuit. Now,
Yeah.
going from here to here, there isn't any voltage at all because that's got zero resistance. V
Okay.
equals IR, R is zero. So you don't have any. But here, going from here to here, V equals IR. You call it I1, and the R is 3. So it's I1 times 3, but it's negative because you're not getting bigger. You're getting, the energy is getting smaller. If the current's going this way, you're losing energy. Do you understand?
Yeah, I see it now.
That's how come that's minus.
Okay.
So you're okay with the rest of it?
Yeah.
Okay. Well, here, let's check it with the power. I mean, everything seems to work out. The volts work, the currents work, but we're going to do the power now. Okay, here goes power. Well, we have three lovely equations for power. Well, why don't we get the power here? Power is equal to IV. So what do we have for a current? It's 3 amps. What's 3 times 24? Oh, gosh. I can't do that in my head. 3 times 24. 3 amps times 24 volts is it 72? Do you get 72 watts?
Yeah.
72 watts. Hey, we got 72 watts. Tell you what, let's put that in green. That'd be good. We'll put the power in. This is 72 watts. Okay, now let's do this one. And again, you can use the other formulas, but we could use this. 9 times 3 is 27 watts. I'll write that out if anybody needs me to. That's 27 watts. Let's see, 6 times, this should be 12 watts. 6 volts times 2 amps. This should be 8 watts. Because it's 2 amps and 2 amps. No, that's wrong. You guys tell me if it's 2 amps and 8 volts, how many watts is that? P equals IV, 2 amps, 8 volts. How many watts is this?
16.
Yeah, it's 16. Good going. 16 watts. Now let's do this one. We got 29 volts and 2 amps. How many watts is that? I get 58 watts. Did I do that right? 29 times 2 is 58, right? Oh, wait a minute, we got this one to do. This one's 5 amps, 15 volts. How many watts is that? Is that 75 watts? 75 watts. All right, let's add them up. Now there's power providers. And what we have 72 watts and 58 watts. That makes a total of, did I do that right? 130 watts total? I think so. And then there's power users. power users. Okay, well, we have the 27 watts and the 12 watts and the 16 watts and the 75 watts. We have 4 users, 1, 2, 3, yeah. Now we're going to add these up. Okay, I'm adding these up now. I believe it's 130, guys. If you add those up, look, you got 130 watts of power that's being supplied and 130 watts of power that's being used. Good, excellent. We have just done a Kirchhoff's law problem, and you can't do that with simplification. Now you could simplify these two. 4 ohms and 3 ohms make 7 ohms, but then that's the end of the simplification. You can't simplify anything else. But you can do it with Kirchhoff's laws. Very, very powerful. Let's do another one. Now, is there any comment or question on any of that?
Well, we're gonna do another Kirchhoff's
Yeah, we
voltage
are.
problem.
We're going to do another one. We sure are.
My question will probably get answered when we do it.
Okay, well, just feel free to speak up at any time. Let me find the one I want here. There's nothing sacred about the way I went around these loops. You could have gone, let me just show you that. You could have gone around this big loop. See, if you went around this great big loop, see that great big loop? Then here's what you'd have for your KVL. You'd have negative 3I1, positive 3I2, positive 4I2, minus 29 plus 24 equals 0. You see what I did? I went around the whole outside, didn't I? That might answer your question there, Zach, if you understand that. See,
Well, so what about the resistor in the middle there?
I didn't even go through it, Zach. I just went around the whole outside. But we've got to include it somehow. So why don't I do this loop here? You're going to have 2 equations because there's 2 unknowns. I'm just showing you that there's nothing sacred about the way I did that. I can go this other way. I can start here, and I can go around this loop this way. That's what I'm going to do. Here goes. If I start here and go here, that's a minus 3I2, and then that's a minus 3I1 plus I2, and this is a plus 29, and this is a minus, it's a minus 4I2, ran out of space there, equals 0. Now, there's 2 equations and 2 unknowns. I wrote them differently, didn't I? But they're perfectly good. And we could solve that. If you want to do the algebra, I will. Just somebody say, solve it, Mr. Griffin, and I'll do it. But you'll get this.
Okay, but all you need is 2 equations. So it can be 2 loops.
Yes.
Any loop, as long as it starts at the same place and ends at the same place.
Exactly.
Huh.
That's right. Good going. That's exactly right. Well, let's do one a little more complicated now. If you guys think you're happy with that. let's say goodbye to that one. And let's do this one here. Now this is problem 1085. In my book, it's on page 493. Here's our circuit. Five ohms, 10 ohms, 15 ohms, 15 ohms, 10 ohms, and 5 ohms. Okay, there's our circuit. Now the first thing we have to do is we have to assign currents, remember? Well, you draw your circuit, did that, and then you have to assign currents. Okay. Now there's more than one way to do this, is the thing about it. But when you do this Thursday night, I think we call this I1. We call this one 2. And so you know what this one would have to be? According to Kirchhoff's current law, it would have to be I1 plus I2. Now here's something a little bit subtle. If I1 comes in here, yeah, here's what we do Thursday night. We're going to call that I3. Now, this one's going to be I2 plus I3, according to Kirchhoff's current law. See, if I2 comes in and I3 comes in, that's I2 plus I3. But now this one's a little bit subtle. This one, what that is I1 minus I3. See, if I1 comes in and part of it goes this way, what's left is I1 minus I3. Now, if you'll add this one and this one, what you'll get is I1 minus I3 plus I2 plus I3, and you wind up with I1 plus I2, which figures, because that's what you got coming through here. This will be I1 plus I2. We just assigned currents. Now, you didn't have to do it that way. We could have assigned them going different directions and given them different names. But when you get all through, you're going to have the same answers no matter how you assign them. Now, in this problem, what did they want us to do? Find the current through each resistor. Well, we'll do that. Okay, yeah. We're going to do this problem. This is a problem in your book. It's got answers in the back. We can check it here in a little bit. And what we got to do now is write KVL equations. Wait a minute. No. We have to assign polarities now. We're not ready to write equations yet. So I'm going to shut up, and hopefully you've got this diagram here, and I want you to put the pluses and minuses in. So you're going to put in some pluses and minuses. I'm going to shut up for a minute, and you put in the pluses and minuses, and then I'll put them in, and we'll see if we agree. Go for it. Actually a little hot. I'm going to open this air conditioning vent here. I'm getting a little warmish. Okay, now I'm going to assign polarities. I should have drawn that a little bigger. It's kind of small, but maybe you can see it. And remember, the way it works is if you have a resistor and the current is going to the right like that, then it's positive here on the left and negative on the right. That's the way the volts are. Always, without exception, resistors can't do it any other way. Now, batteries and capacitors, and when we study inductors later, they the bets are off on those. They can do it a different way, but resistors, you're stuck with this. So therefore, if the current's going this way, this one's plus, this one's minus. If the current's going, now we don't know that the current's going that way. We just assigned it that way. But if the current's going that way, this one's plus, this one's minus. When we get all through, and if we get a negative answer, it just means that the current's going the other way. It's not the end of the world. And this one's plus, this one's minus. See, if the current's going this way, this one's plus, this one's minus. If the current's going this way, this one's plus, this one's minus. If the current's going this way, this one's plus, this one's minus. Now we've assigned polarities. And of course, on the battery, one of my excellent students asked about the battery. The big end there is always the plus end, and that's the minus end. You cannot simplify that circuit and use equivalent circuits. You have to use Kirchhoff's laws in order to solve it. Okay, now the next step. Step number 3 is KVL. See, we've already done KCL. See this I3 and I2, they come together and form I2 plus I3. We've already done the KCL. But now we're going to do KVL. There's 3 unknowns here. There's I1, I2, and I3. We need 3 equations. We need 3 loops. Now, you can do these loops different ways. One way is you could maybe start here and go around this inside loop. Can you guys see how I'm doing that? I'm going around this. You don't have to do it that way, but that's one way. See it? Now another loop you could use is going around this one here. See if this triangle. See it there? We could go around that. That'd be okay. There's more than one way to do this. Another loop, you could go around this as kind of a square. Do you see how I'm going around and around this square? Round and round the square. Those 3 loops I just did would work, and you could solve it with the algebra. Well, let's write these equations and solve them. Here we go. I think I'm going to use this little triangle here. I think I'm just going to go around this little triangle. And I'm going to have a plus 15I1. I went from here to here. And then I'm going to have a minus 10I2. I went from here to here. And I'm going to have a plus 5I3 equals 0. So far, so good. Is everybody happy with that? Let's see who I've got out there. I think it's still my dedicated few. Yeah, it's the ones that have stuck with me through thick and thin here. My 3 excellent students. I just did that little triangle there. I think I'll do this little triangle here. You see this little triangle here? I think I'll do that one. I think I'll start here and go to here. So that'll be plus 10. Now, wait a minute. That's I1 minus I3. And then we have minus 5I3. And then we have minus 15 I2 plus I3 equals 0. And now I need something including the battery. I could do that inside loop, or I could go on the outside. Why don't I go on the outside of the whole dang thing? That'll work. All right, I'm going to start here and go from here. You know what that is? That's a minus 5 I1 plus I2. Now this is going to be nasty and complicated, but it doesn't scare us. We're not scared by this. Plus 20. So you go from here to here, it's plus 20. And I'm going to go around the outside. So that's a minus 10 I2. And then this is a minus 15 I2 plus I3. Equals 0. Stare at that a while and see if I made any mistakes. See if I made any mistakes, which is quite possible. And there's lots of other ways I could have done it. I could have come up here, gone down here, and then crossed over this way and down. As long as you got 3 equations and 3 unknowns, we'll be okay. I think I did those right. Now what do we have to do? Here comes the fun part. We have to, you don't have to do anything with this one. Leave that one alone. But this one here, we're going to have to doctor it up. Let me put them up here. We're going to have to make it nicer. See here we got 10I1. And then we have minus 10I3 minus 5I3. That's minus 15I3. And a minus 15I3. You know what that is? That's minus 30I3. But I'm going to put it here. Minus 30I3 equals 0. Now the I2, we have a minus 15I2. What I've done is I've taken this equation and I've made it pretty. Did I do that right? I think I did.
Looks good so far.
I like it. I'm happy with it. Now I'm going to do this one. I got a minus 5I1. What I'm doing now is I'm taking this equation here and doing a little algebraic magic with it. And you got minus 5I2 minus 10I2. That makes minus 15I2 minus 15. You know what? That's minus 30I2, isn't it? And minus 15I3. I wonder if I did that right. Minus 5I1, minus 5I2 minus 15I2. Yeah, I think I did that right. I don't need these anymore. I'm just going to cross them out. And now I have my three equations and three unknowns. Now here's where I'm going to have to go downstairs and get my calculator that does these. I've got a calculator, and I bet you do too, that can solve three simultaneous linear equations. Get yours out, solve that. I've got to go downstairs and get my calculator. Now, when I was in school, many years ago, we didn't have calculators. They hadn't been invented yet. And they taught us how to do that with determinants. But we don't want to do that. We just want to plug it in. Let me go get my calculator, and you do it. You get the answers. I'll be back with my calculator muy pronto. And we'll get our answers, and we'll see how we did. Okay, well, I found my calculator, and what I need is a thing called simultaneous linear equations, and I'm going to put in my I'm going to put in my numbers now. Wait a minute. Wait a minute. This one's a screw up, guys. I need to have a minus 20 right here. I think I goofed up. You could have gotten a thank you point by pointing that out. You see, did you see that plus 20 there? Well, it makes a minus 20. But I think I did the rest right. 5i1 minus 5i1. That's right. And minus 5i2, minus 10i2, minus 15i2. I think I did that right. Yeah, but I left that off, guys. That was my goof, and I caught it. So I should get the thank you point for that. Somebody out there is going to have to stay awake and help, because I left that minus 20 off, didn't I? Okay, I'm putting these in my calculator now. There's 10 and minus 15 and minus 30 and 0 and minus 5 minus 30 minus 15 and minus 20 and 15 minus 10 5 0. And now I'm going to push this little button that says solve. Hey, this is a lot easier than doing it the old-fashioned way, like we had to do it when I was in school. And here's the answers. I wonder if these are right. This says the answers. I1 is 0.5 amperes. I2 is a bunch of sixes, amperes. And I3 is, gee, I got a minus 0.1, a whole bunch of sixes, amperes. So you know what that means? I3 is going the other way. Well, let's see what the answer book says. This was problem 85. Guys, we just did problem 1085. Go to the back and help me find the answers to it. And they said, chapter 10, number 85. They said I1 is 0.5 amps. Hey, that's what we got. They said I2 is 0.67 amps. Now they rounded off. Shame on them. The book says 0.67 amps. And then I3, they must have labeled theirs different. They got an I3 as 0.67 amps. We labeled ours different than theirs, I guess. Now they do have I5 as 0.17 amps, but it should be a negative 0.17 amps. I think the answer book is wrong on that. It should be, but they never told us which way they're going to have their currents. So maybe their answer, maybe they had their current going the other way. Tell you what, we don't need the stinking answer book. We know how to check our work. We know how to check our work, don't we? Let me turn this thing off to save my battery. There. I turned it off. I'm just curious. Did anybody get those answers? If you did, say uh-huh.
Uh-huh.
Yeah, there's one. How about another uh-huh? We only got one that time. Now, let's check these and make sure they're right. We got plenty of time. I only have 8 o'clock roughly. I need the room though.
I'm trying to get my calculator to do it, so I'm almost done. I gotta
Good
figure
for
out how
you.
to do it.
Take your time. Take your time. I'll make some space here. And what I'm going to do now is I'm going to check our work. See, we don't need no stinking answer book. We can check our own stuff. We can check our own stuff. Now let's check the KCL first of all. I1 and I2, if you add those up, we're going to see if the currents check out. If you add those up, I1 and I2, I can't do that in my head. 0.5 plus a whole bunch of sixes is 1.1, a whole bunch of sixes. That's what we think this current is. Now the current in I1 we think is 0.5. Here, I'll draw it for you. See, it splits. 0.5 amps goes this way, and 0.66, whole bunch of sixes amps goes that way. And coming in, we have 1.1666 amps. And then we said I3, well, we got a minus 1.1666 amps. You know what that means? That means I3 is really going this way, and it's 0.1, a whole bunch of sixes amps going this way. Okay, well, what does that make? Well, let me write that where I can see it better. Going this way, we have 0.1, a whole bunch of sixes. There we go. Now coming down here, this is I2 plus I3. Now I2 plus I3, well, if you do that, let's see what you get. 0.66, a whole bunch of sixes, minus 0.1, a whole bunch of sixes. According to that, this is 0.5 amps. You know what? That works. If 0.6666 comes in, and 0.5 goes out and 0.1666 goes out, they add up. That works. Now let's see what this one is. You know what this one is? It's I1 minus I3. Let's see what that is. I1 minus I3. That's a minus, that's plus 0.1, a whole bunch of sixes. That makes this 0.66, a whole bunch of sixes amps. And see, when you add those together, when you add those together, you get I1 plus I2, which is 1.1, a whole bunch of sixes going this way, and then it goes through this here, and then it goes through the battery, and it comes back over to here. Well, you know what? The currents all work. The currents all work. Now let's get the voltages. I've got the currents and everything, and now we're going to check the voltages. Can you read my diagram. It's a little bit messy. I like my voltages in red. Okay, we're going to get our voltages now, and we're going to see if they add up. See, we don't need an answer book. We can check our own. If you have 5 ohms and 1.166, a whole bunch of sixes and amps, what does that make you?
I got 5.83.
And not that I don't trust you, but let me do it myself. 5 times 1.1, a whole bunch of sixes. Yeah, that's what I'm getting. I'm getting 5.833, a whole bunch of threes, volts on that one. Now we know what this is. It's 20 volts. And now let's get these here. Well, I2 is 0.6666, a bunch of sixes amps there. If that's 10 ohms, wouldn't that make this 6.66 volts? I think it would. Now, if this is 15 ohms and you have a half an amp, I can do that in my head. That's 7.5 volts. Okay, now let's do this one. It's 0.1, a whole bunch of sixes amps, times 5 ohms. I'm getting, this one here is 0.833, a whole bunch of threes, volts. Now the question, see, that's plus minus. It's opposite from the way we set it up, but we didn't know. But now if you take 6 point, bunch of sixes, and add 0.83333, do you get 7.5? Well, I don't know. We'll find out. Take 6 point, a bunch of sixes, and add to it 0.8, a bunch of threes, and let's see what we get. Well, boy, Jove, I'm getting 7.5 volts. If you take this voltage change here from plus minus, and this voltage change here plus minus, it adds up to 7.5 volts. That's good. That's very good. That is checking, everything's checking out, guys. Now let's do this one. We have half of an ampere and 15 volts. I can do that in my head. That's 7.5 volts on that one. Now what's this one? 0.6, a bunch of sixes amps, times 10 ohms. I know what that is. That's 6.66 volts. Okay. Now here's the question. If you take 6 point bunch of sixes and add to it 0.8333, do you get 7.5? Well, we already did that, and it does. It adds up to 7.5. So the volts work. The volts work. Now let's check this out. If you go from here to here, see, this is plus minus, do you understand? But this is minus plus. So what you got there is around, well, I'll figure it out. It's around 13 something. 20. Do you understand? This is plus minus, but this is minus plus. They're acting against each other. Take 20 and subtract 5.8, bunch of threes. Going from here to here, what you've got is 14.1, a whole bunch of sixes, volts. 14 point. Now let's see if that works this way. Going from here up to here. Well, if you take 7.5 and 6 point, a bunch of sixes, does that add up to 14? I don't know. We'll figure it out. if you take 7.5, need a little room here. 7.5, you're going up. Negative plus, 6 point, a whole bunch of sixes, and you add those up. The question is, do you get 14.166? I don't know. Boy, Joe.
Yes, that's what I got.
By Jove, you do. So you see, the volts work going from here to here. Let's do these. Of course, that's the same. 6.66 and 7.5, those are the same numbers. Hey, the volts work. The currents work. The volts work. And now we're going to do the power. I'll put that in green. We need the power on each component. Well, now we got the current. What is the power on that one? See this one here? Well, the volts is 6.666 volts, and the current is 0.666 amps. So we're going to get the power. Here we go. You don't have to use this particular equation. You can use any of the three. They all give you the same thing. I'm getting, strangely enough, I'm going to put it in green. I'm getting a whole bunch of 4s watt. 4.444 watts on that one. Now let me do this one. Now, I don't care which equation you use, but I could just go the current, which is 1/2 amp. I could go I squared R, that would work. What is 1/2 amp squared times 15 ohms? Well, here's what I'm getting. I'm getting 3.75 watts on that one. Now let's get this one. What's the volts? It's a 0.83333 volts. Now, what's the current going through there? Well, it's 0.16666. I know it's going that way, times 0.16666, a bunch of sixes. Okay, here's what I'm getting for that one. I'm getting 0.1388. Need a little room here. 0.1388, a bunch of 8s. I don't know if you can read my writing. It's awfully bad. Let me try to write that bigger and thicker. I'm getting it's 0.1. I'm getting 0.1388, a whole bunch of 8s watts. Now, let me do that again to make sure I'm doing that right. I could go I squared R, 0.1, a whole bunch of 6s squared, times, it was 5 ohms. Yeah, that's right, 0.13888 watts. Now let's get this one. What's the current there? It's 0.5 amps. Hey, look here, 0.5 amps times 7.5 volts. I could almost do that in my head. Is it 3.75? Yeah, I just figured this one out. And I need the room here. Sacrifice this a little bit. I'm getting 3.75 watts. We're doing great. Now let's get this one. What's the current there? It's 0.66666, a bunch of 6s amps. 10 ohms. Why don't I just go I squared R? 0.6, a bunch of 6s squared times 10. Here's what I'm getting for that one. I don't have much room to write it. We'll fit it in here somehow. I'm getting 4.444 watts. Now let's do this one. What do we got in the way of current there? Well, that current is 1.16666 amps. Okay. So let me do that. 1.16, a whole bunch of sixes amps. I'm going to go I squared R. I squared times 5 ohms. Well, I get a goofy answer, but I can't help it. Here's what I'm getting. I'm getting, is this going to show up? Maybe. I'm getting 6.8055 watts on that one. Okay. And finally, let's get this one. We have 20 volts and 1.1666 amps. So the watts on that will be 20 times 1.16, a whole bunch of sixes. I'm getting 23.333 watts. I don't know if you can read that or not, but that's what I'm getting. 23. Okay, now let's total up. I've got 3 minutes left in the class. We've got 3 minutes left, and let's see if this actually works out. Provided. Well, I'm getting 23.333 watts provided. Used. Well, we've got the 6.8055 watts, the 3.75 watts, the 4.444 watts, the 0.13888 watts, the 3.75 watts, and the 4.444 watts. And that's it, isn't it? Let's see, 1, 2, 3, 4, 5, 6. There should be 6 of these. 1, 2, 3, 4, yeah. Okay, add those up and keep your fingers crossed. We only have a minute left. Oh, will we make it? Oh, it's going to be close. Add all that stuff up and hope for the best.
Yep, I got 23.33.
You're kidding. You know what? I got 23.33. Now, to be honest, I got a 2 here, but I think we did good. Guys, I think we did good. It checked out. Hey, we checked our work. We checked the currents. We checked the voltages. We checked the power. And if you don't know how to work that calculator of yours, get your book out and learn how to do it. It's sad, but our time together is coming to an end. Here's your last chance to say anything, but say it fast, because I've got some chili down there that I'm going to heat up. Here's your chance. Nobody said anything. Goodbye, students. I will see
Good
you.
night.
Good night. I'll see you Thursday night for lab.
All right.
Bye, everybody.
Bye.